Welcome back to our little series on generating QR codes using Python. In the last episode, we've already done a lot of the heavy lifting and created these codes. What we are working on here is a version 1 and a version 2 QR code holding the phrase "Hello World." We gave it all of these special patterns here that we can just summarize as the static format, as in the format that is the same for all QR codes independent of the data. The Hello World is stored in these yellow pixels here that are read as 8-bit code words. Now, if this all looks unfamiliar to you, I recommend you watch part 1 where I fully explain all of this in more detail. While these codes look pretty much done, we still have two very important additions to talk about. Well, the first one we kind of already implemented in the first video. There, we generated these error correction code words using the read solo library in Python, but without really explaining them. So in the beginning, I want to take a couple of minutes and explain the topic of error correction. Afterwards, we'll talk about applying masks to our QR codes to finally make them readable. These masks also have something to do with the dynamic format here that we're still missing. So by the end of this video, we'll be able to fully generate QR codes of version 1 and 2. However, if we look at the whole QR code family, consisting of 40 versions, that still leaves us plenty of work for part 3. But now, let's dive into error correction. In part 1 we saw that even something trivial, as not reading the QR code completely flat for example, causes us to lose data. So to combat that, and the loss of data in general, we put these error correction code words in our code. Strictly speaking, they are not necessary for reading data from a QR code, since that is stored separately, but these code words help us read QR codes in day-to-day scenarios. To a degree, they also make the process quicker. So the sacrifice of data space for readability is usually worth it. We'll ignore the exact reasons of why some pixels are read wrong and just treat it as some bits randomly flipping during the scanning process. We're mainly gonna be interested in what happens to these data code words here, since this is the information the QR code stores. In the worst case, if the wrong bits flip, the entire data could become unreadable. So let's focus on these data code words. As we've seen in part 1, for version 1 with quartile error correction, we have 13 8-bit code words. We can think of them as 13 integer numbers between 0 and 255. But that is a lot of bits to keep track of, so let's simplify things a bit. We'll use this imaginary QR code format where the data gets stored as 4 4-bit code words. Now, just as for the original code words, we can interpret them as binary numbers. So in our case, we have 1, 2, 3, and 5 that decode to some data that is stored on this mini QR code. And just like before, they can get corrupted during the reading process. Going forward, we're just gonna move them from the sender side over to the receiver side to symbolize the reading of the QR code. So as you can see, a bit flipped on the third code word and the 3 turned into a 7. But the reader has no way of knowing that this error ever occurred. This is what makes these errors so difficult to deal with. A 7 is just as valid as a 3 in this context of sending numbers. So what can we do about this? Well, the first idea would be to just double the data. If we have twice as much data, we have double the chances of the bits making it through to the other side unscathed. As the receiver, if we compare the two rows, we can be pretty certain that the 2 and the 3 were transmitted correctly. It would be highly unlikely that both numbers flipped bits the exact same way, so we'll assume them as correct. But for the first and the last code words, the pairs don't match. So with this approach, we can at least detect the error, but we still can't fix it. The receiver has no idea which value of the two is the correct one. So here is what we'll try instead. In addition to our 4 code words, we'll send 2 more code words that we'll call A and B for now. The idea is that we set A and B in a way that the numbers follow a pattern. Now, you have to think of the term pattern in a more abstract sense. Normally, our code words won't just magically follow the Fibonacci sequence or something like that. Now, I should say that this explanation of error correction is heavily inspired by Veritasium's video on QR codes. It's a great video that actually also inspired this whole series, so you should definitely check it out if you're also interested in the history of QR codes. It helps if we start thinking of these numbers as the coefficients of a degree 5 polynomial. If we set A and B to 0 for now, this polynomial would look like this. And here we'll implement our pattern. We'll choose A and B so that the polynomial goes through the points 1, 0 and 2, 0. In our case, that would mean setting A to negative 97 and B to 86. Now, these points 1, 0 and 2, 0 are more or less chosen arbitrarily. We could have also chosen 2 different points, but the sender and the receiver obviously have to agree on the points beforehand, otherwise this idea wouldn't work. So we'll set our code words accordingly and send them over to the receiver. Again, he doesn't know if an error in transmission occurred, but now he can check. For this, we'll just take the coefficients we received and plug them back into the polynomial. If all went well, it should go through the points 1, 0 and 2, 0 as agreed. But it doesn't. So somewhere in these 6 code words, an error occurred. But here comes the best part about this method. We can not only tell that an error occurred, we can also pinpoint the wrong number and even find the correct one. Just for a second, we'll ignore the second point 2, 0, and for now only try to get our polynomial to go through 1, 0. For this, we'll go through the coefficients one by one and see how we would need to change them to achieve that. Here, we would need to set the first coefficient to negative 3. Looking at our points, we indeed go through 1, 0. But now the polynomial is kinda curving down and we're missing 2, 0 completely. But that's fine, so the first value wasn't wrong, because changing it just makes the whole thing worse. We'll restore everything to how it was before, and try the same thing with the second coefficient. Here, we need to set it to negative 2. But now we are overshooting and again missing 2, 0. So the second coefficient is also correct. But watch what happens at the third coefficient. If we set it to 3, so that the polynomial goes through 1, 0, we see that it also magically goes through 2, 0. So we just fixed our polynomial. But since the polynomial is going through both points, that means all of the coefficients are correct, and we found the culprit. All we need to do is change the 7 to a 3. And if we compare it to the original message, we indeed fixed the corrupted code word. Now, even though this is a simplified example, I hope you can see how we can extend this concept to more and bigger code words to find and correct errors in the full QR code. But before jumping onto that, I want to implement this simple example in Python. Here, I've written this polynomial class. By inheriting from userList, we tell Python that it's basically just a fancy list, since all we really need for a polynomial are the coefficients and their order. This userList gives us most of the functionality like getting or setting a coefficient. And here I added the mathematical operations we're gonna need. This is by no means a completely rigorous polynomial class, but it has everything we need for now. And here is how we generate the code words. In many explanations of Reed-Solomon codes, you will see this notion of a generator polynomial. This generator is what dictates to what values the polynomial will be 0. So in our example, it was 1 and 2. The way we determine the value of our code words is by dividing the message polynomial through the generator and then returning the negative of the remainder. for anyone interested in the maths, just pause and maybe review these steps yourself. If we run this code, we indeed get our negative 97 and 86 for A and B. We could also increase the number of error correction code words that we want, and with these we could correct for more bit flips. But these numbers start getting incredibly big, so let's just stick to 2. So this system is pretty good, but we still have one issue with it. How do we fit these numbers we get into 4-bit code words? Well, we can work with the negative. We could add a sign bit to all code words, or use 2's complement, or some other solution. But even without it, there is a much bigger issue. We would need at least 7 bits to display these numbers in binary, so they are literally too big for our number system, in which we only deal with numbers 0 through 15. And as we saw before, this issue will just get bigger if we increase the number of code words. But what if we could somehow limit them to this range? So instead of negative 97 and 86, we would have some other numbers here that will still carry the same meaning. This is the part of the video that is gonna get a bit more technical. So if you're happy with this simplified explanation of the error correction, you can skip ahead. For those of you who are interested, I'll still try to keep it as simple as possible. To achieve this limiting of our numbers to 4-bit code words, we have to talk about finite fields, or Galois fields as they are also called. Take the number line of integers for example. There we can do our mathematical operations just like we know them. Now what a finite field does is squish it down to a circle of discrete numbers. And no matter what operation we do on these numbers, they never leave this circle. A very simple version of this would be just to do the modulo operation on every result. If we would do 10 plus 7 equals 17, we take it modulo 16 and get 1. Or 5 minus 13 equals negative 8, modulo 16 equals positive 8. Now, these Galois fields are a bit more complicated. Here we have these weird polynomials instead of numbers, but it still has the same idea. Of course, we're not just limited to 25 numbers, we can easily expand this to, say, 256, but for this I couldn't find an illustration for the Galois field. I've implemented these finite fields in Python through this gfNumber class here. We can set the exact field the numbers should live on with this method, and it defaults to 256. Their mathematical behavior I added through these dunder methods again. If we quickly have a look, we can see that, for example, addition on the Galois field is achieved by XORing the two numbers together. Or that subtraction and addition are the same. Now we can construct polynomials from these numbers. For this, we can inherit a lot from the generic polynomial class we wrote earlier. At initialization, we just convert the input coefficients into these GF numbers. Some methods I did have to update a bit for functionality, but the idea is still the same. We also use a different generated polynomial that is constructed through these exponents, but since its choice was arbitrary to begin with, that doesn't really bother us further. Alright, if we change these polynomials to our new GF polynomials and tweak some other stuff in here, we see that we get a new set of coefficients when we run our code. And indeed they are limited to 4 bits. So we can replace our previous code words with these new ones. Of course, our receiver would also need to use this finite field arithmetic when decoding them, but that doesn't concern us right now. But the best thing about this setup right here is that we can easily change the format. As we know, regular QR codes work in 8-bit code words, so numbers between 0 and 255. We just briefly simplified them for our explanation here. But we can apply the same ideas to this bigger range. All we gotta do in the code is change the field. So instead of 16 numbers, we now have 256, and we also changed this binary mod value here that I'm not gonna go into. If we scale up our example and use the real code words from our original QR code, we get the exact same code words that the read solo library gave us in part 1. I've updated that part of the code to now work with our own code word generation. Alright, that was a lot to take in, I know. If you couldn't really follow, I really don't blame you. I spent multiple hours researching this, and even I don't fully understand Reed-Solomon encoding or Galois fields, but I hope that these error correction code words now seem a bit less magical, and you see that they actually come from a reasonable idea. Time to actually make some progress on our QR codes, because we're still pretty much at the same spot as we were at the end of part 1. Let's tackle the question that probably most of you had after part 1. Why do the two QR codes look nothing alike? Yes, we're missing the format strip here, but even if I copy it over from the finished QR code, the patterns still don't match. And I'll even do you one better. These QR codes both carry the same data. Go ahead, scan them, and you'll see a hello world for both. But again, they look different. But since the data is stored right here, how can these pixels be fundamentally different and still lead to the same data? Well, the answer to both questions are masks. Let's bring back our unfinished QR code, and we'll mark all the pixels that are different in the finished QR code. As we can see, there is a pattern to which pixels got flipped and which stayed the same. If we look around a bit more, we will find 6 more patterns just like these. We call these pattern masks, and you can think of them as a mesh that we lay over our QR code. Any pixels in blue that peek through this mesh are left untouched, while the covered ones in red get inverted. Okay, but why do we even need masks? Now, this is another feature of QR codes that is, strictly speaking, not necessary in a perfect world. However, in practice, we want to maximize the readability of QR codes. For this, we want to keep the codes as noisy as possible. I'm sure you can imagine that the reader will have a harder time finding this QR code carrying all zeros since it's mostly white. Or similarly with this one that is half black. Now yes, these are corner cases, but still theoretically possible. And even in more reasonable codes, we will have this clumping of colors. Here we have some white patches and even a black one over there. Numbers, for example, are assigned lower binary values in the Latin 1 table, so we should be expecting more white pixels that randomly clump together. To break up these patches, we apply masks. As you can see, the codes have become much more noisy. In the simplest case of all white or all black, we get this checkerboard pattern. But usually, the mask is what gives QR codes this seemingly random look, since a lot of the implicit patterns we get through the data get filtered out through the mask. Now, in our code, we can easily apply these masks through their conditions. These patterns emerge from the masking conditions, where I is the index of the column and j the index of the row. If the expression evaluates to true, we invert the pixel at that position. For this, we'll write this method that adds 1 to the value and takes it modulo 2. This has the effect of inverting the current value. And in this masked pixels method, we can check for this condition, and as long as the pixel isn't part of the format, we invert it. Since we have a total of 8 masks, we also need to think about which one to apply. Theoretically, all masks are valid and would lead to a readable QR code. For this reason, we'll just stick to this checkerboard pattern for now, since I feel that it's the easiest to wrap your head around. So I'll just hardcode the 0 for now. However, there is an objectively best mask, and the QR code specifications even tell us how to find it. There are 4 penalty rules that give each mask a score, and in the end, we choose the mask with the best score. I'm planning on adding all the optimization, like automatically choosing the best mask, at the end of part 3. So again, today we just stick to mask 0. We are really close to being done. Looking back to the QR codes from the beginning, we just need to fill out these 30 pixels here. But what exactly do we put there? Well, basically we need to account for all that we've added to our QR code today. We gave it an error correction level that specifies the number of error correction code words, and we masked the data pixels according to a specific mask. But the camera trying to read the matrix, at least right now, has no idea about that. So we need to write down the error correction level and the chosen mask in the format strip. In total, we have 2 strips of 15 bits to fill. We'll focus on only one because the other will just be a copy. We start by putting in the error correction level. If you remember, we already gave them an identifier in part 1, so we can just use that. This fills up the first 2 bits of the strip with 2 ones in the case of quartile error correction. For the mask, we just put down its number. And since they go up to 7, we write them as a 3-bit binary number. Again, we're only gonna be using mask 0 today. Okay, but that leaves us with 10 more empty bits. But we're actually quite happy about that, because just like any other bits, the format information can also corrupt. So we will want to give it its own error correction. Luckily, it works very much the same as the error correction for the data. The only difference here is that we're working with numbers 0 to 1 instead of 0 to 255. So we need to set our field to have a size of 2. Also, we have a different generator polynomial here, but other than that, we can recycle our code from before. In the case of quartile error correction and the checkerboard mask, we get these code words. Now, we're not done quite yet. You see, if we would use mask 0 and medium error correction, the message would be all zeros. And with that, the error correction code words too. And again, we run into this issue of readability. So just in case, we always XOR it with this string. You can kind of think of it as a mask of its own. XORing with a 0 leaves it the same, and XORing with a 1 inverts the bit, just like our masks. Also, let's change it back to our initial format strip so we see the result we need. Now, as I said before, to further protect the format strip against corruption, we simply duplicate it and place it in these empty strips here. Here is the code to generate the format strip. And now, all we gotta do is implement it into our existing addFormatStrip method that, up until now, only marked it as part of the format. And with this, we are finished. We've implemented all the necessary logic to fully generate our QR codes. For now, we still have to input all the parameters manually. As I said, in part 3 we'll also work on some optimizations, where we'll let the QR code decide the best encoding mode, smallest version, and so on. But it works. For example, here is our old friend, the Hello World code. Or with version 2 and low error correction, I can barely encode the YouTube link to my channel. But really, we can encode anything we like. It doesn't even have to be a link. We're getting really close to the end of this deep dive into QR codes. Right now, our biggest enemy is capacity. As I mentioned in part 1, we're still unable to generate QR codes larger than version 2. So even in the most restricted case of numeric encoding and low error correction, we're limited to only 77 characters. If we try to go bigger, right now it would be unreadable. This is because the format changes a bit for larger QR codes. Mainly, they have more alignment patterns that we can't generate yet. So we'll take care of that in the next episode, along with all the optimization I've been promising this video. So thank you very much for watching, and I hope to see you in part 3.